All right, here's the proof of the product rule. So if I have a function that is a product of two other functions, right? So I have g of x times m of x, and that's what f of x equals. So I'm going to go back to our origins, right? Like the limit definition, and we'll come back to this a lot for different proofs and things like that. So if I start with the limit definition, I say, okay, well, the limit definition of the derivative, to be more clear, and let's apply that to this situation, right? So if I turn this into f of x plus h minus f of x all over h, let's see what that would look like. So f prime of x, I'm going to start out with f of x plus h, so I'm going to put x plus h in here for x, right? So it's going to be g of x plus h times m of x plus h, right? So this is f of x plus h right here, okay? F of x plus h, okay? And then next, I'm gonna subtract f of x, and f of x is just this right here, right? It's just g of x times m of x, okay? So this is f of x. All right, so that's f of x plus h minus f of x, and then it's all over h. All right, so no big deal, right? So that's basically what it looks like when we just plug everything in, right? Into the limit definition of the derivative. All right. All right, so now we're going to algebraically manipulate this a little bit, and we're going to do a tricky thing, and this isn't so obvious. What I'm going to do is I'm going to add in a plus g of x times m of x plus h. Okay. Now, remember that I can't just add anything I want to a value, right? If it's an equation, I could add to both sides, but I don't really want to add to the other side, because that's what I want to end up with is f prime, right? So I don't want to put something else on that side. So another way to balance out something, instead of adding something to both sides of an equation, you can add and subtract the same thing to the same side of an equation or to an expression. Okay, so if I add and subtract the same thing, then I end up with a net with zero net change, right? It ends up being the same as what I started with. All right, and then I'm going to bring down this as well. Okay. All right. So, and you'll see, I think, in a second why we do that, why we do what we just did. So, and actually what I want to do is I want to switch these around to where this is actually the minus and this one is the plus. Okay. All right. And so now what I can do is I can, first of all, I'm going to do a couple things at once here. First of all, I'm going to break this fraction into two parts. Okay. So I'm going to make one fraction over h plus another fraction over h. All right. Okay. And then what I'm going to do is I'm going to factor out, in this case, an m plus h, right? So here I have m plus h in common with m plus h. So what I'm going to do is I'm going to put that m plus h in the front, m of x plus h, I should say, I'm sorry. Okay. And so then what I'll have left over inside the parentheses is g of x plus h minus g of x, right? Okay. So then on this side, what I have in common is a g of x, right? So I'm going to factor out a g of x. So I'm going to put a g of x on the outside. And then inside the parentheses, I'm going to put m times x plus m of x plus h minus, right, because that minus there, and then m of x. All right. And so now what? What I forgot actually at the very initial part here is the limit as h approaches 0, right? And so that limit should also be here, of course, and finally here, right? And it's of this whole entire expression. Okay, and now we can apply our limit laws, right? We know our limit rules. We know that the limit of a sum is equal to the sum of its limits, right? And so I can apply the limit to this and to this independently. And then we also know that we have a product law or product rule of limits, right? Where the limit of a product is equal to the product of its limits, right? So I can say the limit as h approaches 0 of m of x plus h, I can isolate that, times the limit as h approaches 0 of g of x plus h minus g of x all over h, right? Plus the limit as h approaches 0 of g of x times the limit as h approaches 0 of m of x plus h minus m of x all over h. Okay? All right, so basically I just split these up, right? I split this up and made it a product of this times this, right? And the same thing with this. Okay? All right, now some of this should look familiar, right? This right here and this right here, if you notice, is the definition of the derivative, right? It's the limit definition of the derivative. It's just with different letters, right? So this here is by definition g primed of x, right? G of x plus h minus g of x all over h as h approaches 0. That's g primed of x, okay? And similarly, this is m primed of x, right? This is the limit definition. This whole thing is a limit definition of m primed of x. All right, so that's what those turn into. And then here, as h approaches 0, right? As h approaches 0, what will happen is x plus h as h approaches 0 is just going to be x. And so this will just turn into regular m of x. Okay, bring down the multiplication symbol there. Bring down the plus. And then this, the limit as h approaches 0 of g of x, there's not even h in there, so that's just going to remain g of x. Okay, and so there's our product rule. So let's put it all together. So f primed of x, what we started with on the left, is equal to one function times the prime of the other plus the other function times the prime, right? Okay, so it's one function times the derivative of the other times the derivative of the one function times the regular other, right? Okay. All right, and the way that we see it here, and this is how you see it a lot of times, is if we take the derivative of f times g of f of x times g of x, we'll get f prime g plus g prime to f. Okay, or sometimes you'll see it as f prime g plus f g prime. That's usually the way actually I remember it. So f prime g plus f g prime. All right, so it's the derivative of one times the regular other plus the derivative of the other plus the regular function, the regular other function. So that is the proof of the product rule of derivatives, okay? So it's not just, you can't just take the derivative of one and multiply it by the derivative of the other. It's not that simple. We actually have a formula that we have to adhere to, right? Which is, once again, the derivative of one times the other, and then the derivative of the other times the one,